Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 6th lecture on the course titled Maritime Structures Under Fire, Blast and Explosion, offered by the Department of Maritime Engineering at IIT Gandhinagar under the SwayamPrabha courses. Maritime structures are subjected to high vulnerability of fire and accidental loads. For example, in the recent scenario of large quantum of LPG being downloaded in the Gujarat coast, for example 45,000 tons of LPG which has got to be embarked at 1000 tons of LPG per hour. So look at the operational scenario at which this has to happen, and 2 vessels of a very large size of each this capacity has to be offloaded on the port. Apart from managing the logistics of the port, the main concern here is we are handling a huge fuel of very vulnerable in nature. So any small spark or any mishap accidents happen during this sector of time will cost a lot of trouble to the port as well as to the public and environmental issues. So friends, it is very obvious that maritime structures under emergency rescue operation are always subjected to vulnerable activities, either imposed by nature or by demanding operations such as what is now currently happening. So therefore friends, it is very important for a maritime engineer to understand how to design these structures when they are exposed to special loads such as fire, blast and explosion. So welcome to lecture 6, which is a sequel lecture on the materials for maritime construction 2 on this course. So friends, in the last lecture we discussed about materials which are most preferred for maritime construction. We converged to saying that steel is one of the most preferred material for maritime construction. However, there are other alternate materials such as concrete, rubble masonry stones, asphalt blocks, etc., which are also used for different applications as we saw in coastal and other kinds of structures. When we talk about steel as a most preferred material for construction, then steel should be looked into a closer window at its properties when subjected to high temperature, because we are talking about a risk of fire, blast and explosion, which can all cause increase in temperature during such events. So friends, let us take an example of explaining carbon steel and alloying elements. There are 3 types of carbon steel, namely low, medium and high carbon steel. Each type varies significantly in its properties. The designation of carbon steel is indexed as 10XX. The XX percentage indicates percentage of carbon content, and 1006 for example tells me that it has got a carbon content of 0.06 percentage. Carbon content higher than 0.3 decreases its weldability below the desired value. Low carbon steel has carbon content approximately in the range of 0.05 to 0.3%. It has pretty high weldability and workability, but low hardenability, machinability, strength to weight ratio and wear and tear resistance. So friends, the alloying elements in steel alters the mechanical properties of steel in a significant digit. If we talk about medium carbon steel, then this has got carbon content ranging from 0.3 to 0.6%. It has medium to low weldability, high to medium surface hardening, strength weight ratio and machinability. Therefore, these kind of steel, for example medium carbon steel, has specific applications. They are applied to crankshafts in ships and drill vessels and couplings in risers, pipelines, etc. Whereas look at high carbon steel, the carbon content in this particular grade of steel is pretty high, can go as high as 1%. Therefore, as a result, it possesses very low weldability, very low machinability and workability, but has a very high hardenability, strength weight ratio and wear and tear resistance. So, you have a gain, you have a loss. So, as a maritime engineer, as a material specialist recommending materials for maritime structures, one should understand the pros and cons of the alloying elements added to steel, though we never consider steel as such a varied classifications in any other form of construction, but in maritime industry choice of material matters a lot. So, if you look at high carbon steel, it has got very specific vertical applications such as springs, alloying elements and cutting tools. It is not useful generally for conventional construction. So, in general friends, the offshore platforms are usually constructed and fabricated with low carbon steel, okay, or to a greater extent medium carbon steel, but never high carbon steel. Now, let us look at what are the specific alloying elements which are added in steel manufacturing and what are their hands in reducing or increasing certain vital mechanical parameters of steel. Alloying elements influence the mechanical properties to a significant number. For example, aluminum improves case hardening through nitriding, bismuth improves machinability, boron improves hardenability, chromium improves hardenability, and it is a very good candidate for corrosion resistance. In maritime environment, corrosion is one of the serious concerns which we have in all steel structures. Copper improves again corrosion resistance and lead improves machinability. So, varying alloying elements have different contributions, different roles to play in vital mechanical properties of steel. They also have some functional values to be played in steel when used for specific applications in maritime sector. Having said this, let us further add some more list to these alloying elements and see their consequences or their benefits in the mechanical properties of steel. Manganese, if added as an alloying element to steel manufacturing, reduces brittleness. It removes excess oxygen and therefore increases hardenability. Molybdenum improves toughness. We discussed about the measurement index of toughness, why and how this is important in steel as a material of construction in maritime sector. Nickel improves toughness and corrosion resistance. Silicon improves strength. Sulfur improves machining. Titanium reduces martensitic hardness in chromium steel. Tungsten increases melting point, can be a good candidate when used at high temperature. Vanadium improves strength and ductility and also increases toughness at high temperature. So, gradually friends, you will also notice that we are exposing you to certain alloying elements where the steel characteristics are significantly questioned at high temperature. After adding alloying elements to steel, one of the primary concerns in fabricating steel structures is it weldable or not? Weldability is a very important characteristic of any construction material because it enables me to fabricate the structure or not. So, weldability of steel depends of course on alloying elements. So, weldability can be always checked by an equation called carbon equivalency. The carbon equivalency as a sample is given here. Carbon equivalency can be computed as a percentage of alloying elements present in steel, like certain percentage of carbon, certain percentage by 6 of manganese, nickel, copper, chromium, molybdenum, vanadium. We can see that these all together by some fraction adds to carbon equivalency. Now, let us come to the question, what is carbon equivalency? Carbon equivalency helps to predict weldability of steel by combining the hardening effects of carbon and other alloying elements. Low carbon equivalency means good weldability. Okay? Higher indicates a greater risk of cracking, especially in heat affected zone during welding. We call this as powder formation in metallurgical perspective. After welding at high heat affected zones, if the carbon equivalency is higher, you will see the joint starts cracking. So, the weldable effect will not retain for a longer time. Once you have weldable connections cracking, it starts corrosion. We call this as pitting corrosion or crevice corrosion. So, these are all very important negative aspects which one did not expect at the connections, especially because we already know any tubular or any construction member will always have its weakness at its joints or connections. So, higher carbon equivalency indicates a tendency to harden and becoming brittle after welding. So, one has got to be very careful in checking the carbon equivalency, which is actually a percentage of contribution from various alloying elements, adding to it to compute equivalency. It becomes more susceptible to hydrogen induced cold cracking if carbon equivalency is higher. So, friends, if you look at a cutoff value, the weldability excellence depends up to 0.35 of carbon equivalency. So, carbon equivalency therefore helps to determine if preheating is necessary to avoid weld defects. If carbon equivalency less than 0.4, excellent weldability, preheating is not required. If it is between 0.4 and 0.6, it has landed in moderate weldability, preheating is recommended, whereas if carbon equivalency crosses 0.6, weldability is very poor, preheating at about 200 degrees Celsius is compulsory if you want to do welding. Once you obtain carbon equivalency, this table helps me to comment upon its weldability. If the carbon equivalency worked out from a sample equation like this is computed, which is contributed from various alloying elements, if that value is up to 0.35, I can say the carbon equivalency 0.35 recommends to excellent weldability. Similarly, as the carbon equivalency keeps on increasing from 0.35 to 0.5, weldability keeps on dropping from excellent to poor condition. So, it is very important, friends, that before you choose steel or grade of steel or classification of steel for maritime construction, please pay attention. Apart from its strength and Young's modulus, also pay attention to the alloying elements of steel, because they will dominate whether the weldability is possible for this member or material. Having said this, carbon equivalency is a point of debate in research. Many institutions and many academia and industries have come up with their own equations of working out carbon equivalency. Let us quickly look at them and see and understand which is important. Let us say, look at this International Institute of Welding. Carbon equivalency is given by this equation, which is recommended by International Institute of Welding. So, it depends upon carbon percentage, manganese, nickel, copper, chromium, molybdenum, vanadium by some fractions as you see on the screen. Okay. Alternatively, you also have Japanese Welding Institute gives me the carbon equivalency, where it has added contributions from silicon, copper, chromium, nickel, boron, vanadium and molybdenum. Durand-CM, which is being used, carbon equivalency method is being used in Dutch as well as in German, are being also given in this equation here, which also has percentage alloying elements added from silicon, copper, manganese, chromium, vanadium, molybdenum and nickel. Thyssen CET, which is another equation alternate for carbon equivalency, has got contributions from molybdenum, manganese, chromium, copper and nickel. Friends, the alloying elements chosen by different equations are all dependent on the experimental studies conducted by their research group, and therefore, they have got variety of explanations given. I am not a metallurgist, therefore, it is very difficult for me to comment upon why and how these ingredient alloys are chosen for working out carbon equivalency. What I know from the commentary of the code, we know that they are all based upon extensive research conducted by different institutions, therefore, honoring the research content and the valuable inputs given to the industria and academia, we believe that we can have a choice to use any one of these equations to compute. However, standard equations also refer to what we see in Eurocode. Eurocode gives me carbon equivalency based on this, where it is function of carbon, manganese, copper, nickel, chromium, molybdenum, vanadium, which you will see is more or less similar to International Institute of Welding. Okay? It is more or less same. So, most of the codes agree on at least the choice of alloying elements to compute carbon equivalency. Of course, a few of them vary. we add more alloying elements. Now the question obviously comes, why do we have so many equations? New developments of modern steel with new alloying elements keep on adding. For example, we have functionally graded materials which can also have constituent alloys added to it to improve the strength and corrosion resistance of steel. So, though we do not discuss about FGM applications in maritime industry in this course, there are separate references available. There is a book written by me on FGM use on maritime structures. Please look at that reference and you will know FGM has contributed a lot to improve the strength and corrosion resistance of risers, especially marine risers, and therefore, when lot of new alloying elements are added to steel manufacturing, obviously the weldability becomes a question. Therefore, the institutions have come up with different contributions of varying alloying elements, therefore, we have so many equations. Okay? Then the question next comes, as a designer, which equation should I use? Most commonly friends, metallurgists all over the world and maritime engineers recommend IIW equation, which is similar to Eurocode equation for computing carbon equivalency. If carbon equivalency is less than 0.11% by weight, one can use then the Japanese equation. Okay? So, therefore, friends, after we compute the carbon equivalency, we can refer to this table and say, comment whether the weldability is falling in which category of this record. So, we need to have a good or very good weldability before we start using them for maritime construction. So, friends, we learnt a very important lesson at this point in this course, that selecting steel as a construction material alone, looking at its strength, Young's modulus, will not help to design the member, because we are looking for different forms, different types of construction of maritime structures. Therefore, though steel is one of the most preferred material for construction, but before choosing a type of steel, grade of steel and classification of steel, please also pay attention to the alloying elements present in steel, because they will govern the weldability. Furthermore, we also saw alloying elements also alter the mechanical properties of steel. So, be very careful before you land up in using or choosing a specific grade of steel for maritime construction. Having said this, let us now look at steel, maybe a low carbon steel, for example, at high temperature. So, let us look at very important points in this context. Friends, steel is one of the most preferred construction material for maritime industry. I mean, undoubtedly, this is a very valid statement. What makes it to be a very common candidate? Its high strength, its good ductility. Okay. What do you understand by ductility? For our recap, let us say if this is my stress strain curve of steel, if I try to compute the strain at ultimate by strain at yield, the ratio of strain ultimate at strain yield is called ductility ratio. If ductility ratio is high, it means steel is very good and very ductile. Okay. Similarly, friends, the ratio of ultimate stress or strength by yield strength, ultimate strength by yield strength is called strength ratio. For a typical steel, you will notice that the strength ratio will be in the order of 2, whereas ductility ratio will be in the order of 6 to 8 for good steel, good grade of steel. Okay. So, it means this curve has got a long horizontal plateau compared to a very less vertical plateau. Okay. So, typically the curve is like this. Okay. Very long horizontal plateau compared to very less vertical plateau. Okay. Now, we understand that high strength, good ductility and ease of fabrication. What I can put this as good weldability. Okay. Make steel as one of the most preferred material, but in high temperature at elevated temperature, the mechanical and thermal properties of steel deteriorate. Okay, they degrade. So, let us look at Young's modulus. It reduces progressively with temperature. Let us look at this curve. So, the red line is indicating the red line is indicating the variation in modulus of elasticity or Young's modulus with respect to temperature. So, you have a plot where temperature is varying from 0 to 1200 degrees Celsius, whereas the y axis plots the reduction factor. So, from this figure you will notice that Young's modulus reduces progressively at around 600 degrees Celsius. Okay. It falls to a value of less than 30%. So, 70% of its strength is lost at 600, whereas in maritime construction, especially under fire of hydrocarbon, the temperature reaches as high as 1200 degrees Celsius. So, practically friends, at 1200 degrees Celsius, the yield value or the modulus of elasticity is practically 0. It means the steel has started flowing. There is no strength availability in material at all. Okay. So, around 600 you will notice that the reduction factor is 0.3. So, 70% of the strength is lost. Okay, that is very important. Look at the yield strength. Yield strength is plotted in blue color. There is a plateau, then it significantly falls and bumps to 0. So, up to, for example, let us say 400 degree, yield strength is not affected at all. So, no worry about that. Okay. But after a marginal increase beyond 400, yield strength drastically and significantly falls and practically it becomes essentially 0 at 800. 90% strength is lost. Okay. The steel loses its strength as the temperature crosses 400 degrees Celsius, the yield strength, and the drop or the degradation is significant. Look at the proportional limit of proportionality where we confirm the material remains elastic, which is indicated by yellow line, okay, up to 150 or 100, let us say, no variation. When it even crosses 100, it starts decreasing. So, friends, at a temperature about 400, the proportionality or elasticity is lost completely. 50% is lost, 50% at least, the steel starts becoming plastic. So, friends, these are very important information which we must give as an input when we start doing the design for maritime construction. So, friends, properties at high temperature, as you see on the screen, are very important because proportional limit shows decreasing trend similar to yield strength and becomes negligible beyond 700. It is noted that the critical temperature for structural steel is taken often at 550 degrees Celsius. beyond which the strength loss is significant. So, 550 is somewhere here, is here. If we draw this vertical line, let us say I will draw it. If we draw the 550 vertical line, for example, and pick up the intercepts of each one of them, okay, these are my reduction factors appropriately applied to yield strength, to modulus of elasticity and limit of proportionality. So, I must use these factors while I am doing numerical modeling as an input in fire resistant design of maritime structures. Having said this, we also have a MATLAB code which is on the screen now. You can just simply copy paste this code and run on MATLAB window, editor window, and run the program. You will get typically these curves. Okay. So, for the benefit of learners and viewers, even we believe that the complete dissemination of knowledge is important. Therefore, we are given also the MATLAB code which will help you to plot the reduction factors of steel under elevated temperatures. Having said this, why this kind of variation or reduction factor is important in design? When conducting a finite element analysis to assess structural performance of structures under high temperature, these reduction factors must be applied as an input to the material property at each time step of your analysis. For instance, instead of using ambient temperature yield strength, it should be multiplied with the corresponding yield strength with a reduction factor at a simulated temperature. Similarly, friends, modulus of elasticity and proportional limit should also be scaled down using respective reduction factors. This ensures that the simulation reflects the true thermal mechanical response of the material under fire exposure, avoiding unrealistic overestimations of strength and stiffness. Failure to incorporate these values or these temperature effects on the mechanical properties can lead to inaccurate results, undermining the reliability of structural fire design. Therefore, these reduction factors are not optional, they are compulsory, they are essential to be used in the core, safety driven, realistic predictions of material behavior under fire exposed structures. It is very important that we should follow them. Structural steel in particular undergoes significant degradation in both strength and stiffness to higher temperatures. Mechanical properties become time dependent and temperature dependent, influencing both the load carrying capacity and deformation characteristics. You can ask me a question, what are the consequences of using steel at higher temperature? When the material exhibits reduction factors on its strength and mechanical properties, these are the consequences. For example, reduction in elastic modulus leads to increased deflection. Decrease in yield and ultimate strength reduces resistance to applied loads. Increased ductility, especially at higher temperatures, reaches recrystallization range. Modified strain hardening behavior affects post yield performance of material. So, very particularly many of these temperature and time dependent characteristics of mechanical properties play a very important role intelligently in engineering design of maritime structures. Having said this, let us now try to plot or show you a plot of low carbon steel, the stress strain curve. If you look at the stress strain curve of low carbon steel, which is now plotted at every temperature difference of 100 degrees, starting from 100 to 800. So, the conventional, let us say low carbon steel, where we are only worried about the yield strength part. Beyond the yield plateau, we are not plotting this curve. Okay, beyond the yield plateau, we are not interested, because in all design procedures, we always limit our stress to yield strength. So, when you look at the steel at 100 degrees Celsius, which is here, okay, and the strength is about 650 megapascal. I am talking about the yield strength, okay, 650 megapascal. Use a factor of 0.85, you will land up in around 600 or 585. Agreed, no issue. But when you increase the temperature by 100, it falls significantly to 500. As you keep on increasing temperature to 800, it practically gets 0. So, friends, even a conventional stress strain curve is temperature dependent. We have not been understanding this in detail when we have been using this for fire resistant design in earlier structures. But in maritime structures, since the maritime structural operation and functions all depends on high risk involvement in terms of fire, blast and explosion, it is important that we must realize the material characteristics variation with respect to temperature, which is on the screen at this moment. So, it is important that, okay, let us write down the comments here. The mechanical properties vary significantly at high temperatures. We already saw that. Okay. At 100 degrees Celsius, the material behavior closely resembles ambient conditions, but the curve begins steep slope in the linear portion, indicating high reduction in E. You see the slope of the line changes. From this, it changes here. So, there is a steep reduction in E, Young's modulus. Okay? There is a steep reduction in modulus of elasticity. Furthermore, friends, you will notice that a distinct yield point which is necessary, is becoming relatively unstable at high temperature. You see, most of these curves do not have your distinct yield point. One can use 0.2% proof test to find out that. That is an approximate method, but they do not have an yield plateau. You will see there are no yield plateaus. This has an yield plateau, but the yield plateau is lost as you increase the temperature. Okay, with the increase in temperature, because this is 800 and this is 100, with the increase in temperature, yield plateau is getting lost. Okay, the distinct yield point as observed in 100 degree ambient condition is now lost. This means when you lose an yield plateau, lost at high temperatures. Okay. So, what is the consequence of this? This plateau actually signifies the ability of steel to undergo significant strain without corresponding increase in stress. They are not. This is one of the key feature. This is one of the key feature which is necessary when you talk about structures under seismic and accidental loading, such as impact, explosion, blast, drop objects, etc. It's very important. So, this feature is missing as you go with higher temperature. Okay. This behavior is desirable in structural applications of maritime structures. It ensures predictable yielding and allows redistribution of moments or forces internally before failure, and this advantage is lost when you use steel at high temperature. So, for example, when the temperature ranges 300 to 400 degrees Celsius, you will notice that the initial slope declines. Okay, see here, the initial slope 300 to 400 degree, that is the orange line and the yellow line. You will see the initial slope declines. You can see that it is a variation, right. This initial slope is an indicator of Young's modulus. It means Young's modulus drops significantly. Okay. Structures under this condition experience large deformation. Large deformation under the same load. So, therefore, the elastic property in design does not mean anything because steel does not give you that range of strength. Okay. And furthermore, the yield plateau becomes shorter and less prominent. This change suggests a loss of well defined yield point. Okay. The transition to plastic behavior becomes smoother and less abrupt, making it difficult to identify a clear yield stress for design and analysis purposes. When the temperature is 600, degree and beyond, material enters a severe thermal gradation undergoes a severe thermal degradation. The stress strain curve becomes increasingly shallow, peak of the strength is lost and stiffness have dropped significantly. However, the strain at failure tends to increase, which implies that the material becomes extremely ductile. Material becomes, undesirably ductile. Okay, we do not want that ductility. The ductility allows large deformation before rupture, that is very important. Before rupture, but the load carrying capacity is greatly compromised. Okay, friends. So, at this stage, steel would not be able to resist any substantial loads acting onto it. When it reaches beyond 800 degree, it is completely lost and steel cannot be used for anything. Okay. Now, let us move on to the next property, which is the Poisson's ratio. So, as you see on the screen, Poisson's ratio also increases when the temperature increases. Okay? So, like structural steels lost, isotropic material like steel, Poisson's ratio typically lies in the range of 0.27 to 0.33 in room temperature. Okay? It is used in stress analysis, constitutive modeling, finite element simulation, particularly when the member is under 3-dimensional stress state. But under elevated temperature, as you see on the screen, the material deformation is no longer purely elastic or linear. The Poisson effect becomes more pronounced due to thermal expansion, creep and softening. So, Poisson effect increases due to thermal expansion, creep and softening. Although Poisson's ratio is often assumed to be constant in standard design, experimental data shows that it increases the temperature, as you see on the screen here. It reflects internal deformation mechanisms. So, it reflects undesirable internal deformation mechanisms. So, it is not a simple number to be used. So, be very careful about this. Now, up to let us say 200 degrees Celsius, it is almost constant. Let us say the value is about 0.3. This aligns with standard design procedure. Around 400, it increases to 0.31, the marginal observation. Okay. So, this is going to cause thermal softening. And it will increase lateral deformation. Poisson ratio is a ratio of lateral to longitudinal, we know that. So, now from 600 to 1000, from 600 to 1000 degrees Celsius, you will see there is a steep rise of Poisson's ratio to 0.35. This is a clear indicator the material becomes more susceptible to lateral strain under axial stress. This is a very dangerous issue. So, you apply axial stress, okay, but the lateral strain is increasing. So, this is a very undesirable and unexpected design purpose. When the temperature is about 1200, then Poisson's ratio reaches 0.42, suggesting that the material or the member has undergone inelastic deformation. And the material's microstructure is highly unstable. It's become highly unstable. Therefore, such a rise in Poisson's ratio is not desirable and should be taken care of in this. So, therefore, friends, temperature dependent Poisson's ratio ensures better understanding of 1. Lateral deformation, 2. Stress redistribution, 3. Crack initiation and spalling. And 4th, structural collapse modes. So, incorporating such detailed material property helps to understand and make the model more real and reliability of structural, thermal, finite element analysis in fire safety engineering. Furthermore, let us talk about the specific heat of steel, carbon steel, and thermal conductivity of steel as you see on the screen. With the increase in temperature, let us talk about the specific heat in general. You will notice that the specific heat governs the structural member, how much energy is required to raise its temperature, and this value typically varies with temperature. You will notice that there is a steep increase in the specific heat at a specific value of around 730 degrees Celsius. So, it is a critical temperature at which the specific heat increases significantly in steel, up to which it is not, beyond which it is not. Okay? So, it has got a very different phase transformation effects in structural design. Coming to thermal conductivity, thermal conductivity controls the rate at which heat is transferred through the material, conduction, right. For steel and concrete, conductivity generally decreases as temperature increases, slowing down the internal heat transfer. If these variations are not captured correctly, the predicted temperature distribution within structural elements will be inaccurate. Therefore, detailed fire thermal structural analysis will become wrong if you are going to use this beyond 800 degrees Celsius. And I am talking about a typical fire accident where the temperature reaches as high as 1200 degrees Celsius. So, a typical program, MATLAB program is also available for you to plot the variations in thermal strain versus temperature. You can simply use this and plot the variation of thermal conductivity and other things. Friends, as a summary, material selection governs effective and efficient functionality of maritime structure. Steel, of course, the most preferred material. Crowe classifies them in many ways. Strength is not the only criteria. Weldability, formability, through thickness stresses govern the design. Most importantly, strength weight ratio, which is usually a check in design, does not apply to maritime structures. It is governed by both strength and stiffness. In addition, weldability governs material selection. Alloying elements of steel controls various properties, weldability and strength. Corrosion resistance, fatigue strength and fabricability are equally important. Maritime structures focus on prevention maintenance. Therefore, continuous health monitoring becomes very mandatory. Maritime structures are generally repaired when they are loaded. Therefore, careful selection of material is very vital. Material strength is also affected by service temperature. Charpy test results are temperature dependent. Alloying elements vary steel behavior significantly. Strength, ductility, modulus of elasticity change significantly with temperature, friends. Friends, I also have a design exercise for you. You can try to do this as a self-learning exercise. We have taken 3 grades of steel, S355, 420, 460, where this number indicates the yield strength. Okay? S indicates steel. So, the alloying elements percentage of this composition is given. Carbon, silicon, manganese, phosphorus, sulfur, aluminum, all these are given. Okay? I want you to work out the weldability. Also, refer to international codes of design practice and try to find out they belong to which group of steel. Okay? So, it is a self-learning exercise for you. Please do this and then comment upon this for a self-learning purpose. Friends, we come to the end of this lecture. Hope you have followed the sequel of both material 1, material 2, which are very interesting and they are very specific to maritime structures. Thank you very much. Namaste.